and hear me?
Yes.
Okay, thanks for the organizers of the special issue, and thanks to the organizers of the webinar for giving the chance to present this tutorial on next generation multiple access from basic principles to modern architectures. And so if you want to understand the basic limits of the multi-user communication challenges that were introduced before, then it's a very good way to look at the basis, and that is from network information theory. And there we can understand what are the ultimate data rates that can be supported reliably. And usually, if you have a course on network information theory, you would start with a point-to-point channel shown on the upper left side, where we know that this point-to-point channel, even if we have fading and additive white Gaussian noise, we can achieve the capacity by using so-called point-to-point Gaussian codebooks at the transmitter, and then we have a usual point-to-point decoder at the receiver, and then we get this well-known Shannon capacity for the point-to-point link. Now, if we look at a scenario with two transmitters and one receiver shown at the right upper side, which is a standard multiple access channel or uplink channel, then the best strategy and to achieve the capacity region of this channel is to allow both users to transmit at the same time on the same frequency in the same resource block and apply at the decoder something that was introduced already in the last presentation, which is called successive interference cancellation. So the receiver in this case can decide the order how to decode the signals of the two users. Interestingly, for the single antenna case, there is no difference if we choose different decoding orders. So the decoding order can be chosen by the receiver and can be anything. In order to achieve the complete capacity region, which is this pentagon here on the right-hand side, what is needed is time sharing between these two operating points indicated by the circles. Time sharing means that we will transmit a certain percentage of the code word using one strategy and then switch to the next one. What is also well known is the capacity region of the broadcast channel. This is the scenario where we have one transmitter and two receivers. And here, in this case, we have a so-called degraded broadcast channel. This means that the two receivers can be put in a specific order. So we have one receiver which is stronger and has a stronger channel, and another receiver which is weaker. And for this channel, for this broadcast channel, it is well known that the optimal strategy is to apply superposition coding, so encode both messages for both users on the same time at the same frequency, and then perform successive interference cancellation at the stronger user and perform treating interference as noise at the weaker user. This is what was introduced in the last presentation, so-called power domain non-orthogonal multiple access, PD-NOMA. Here again, it is important to note that this combination of point-to-point channel codes together with superposition coding and successive interference cancellation can achieve the capacity region of this system. Now on the right-hand side, we see the interference channel, and here the situation is different. We do not know the capacity region of this channel, so for a very long time, this is an open problem in network information theory. However, what is known is that point-to-point codes in combination with a technique that is called rate splitting, treating interference as noise, successive interference cancellation, and using time sharing either achieves the capacity region if the interference is strong or very strong, or if the interference is very weak, or it is the best known achievable rate region. So for this interference channel, we are still lacking the complete characterization of the capacity region, but we already have many pieces of the puzzle available. Now, if we move to more practical systems, which apply either some multi-carrier scheme for their transmission, like orthogonal frequency division, multiplexing, OFDM, or we move to multiple antenna systems, then we have to be very careful if we want to apply the network information theoretic results from the last slide directly to these systems. For example, if we have multiple carrier systems, one fundamental question is if we can improve the capacity region if we code over these parallel channels simultaneously. So if we have a parallel multiple access channel or parallel broadcast channel, then it turns out that they can be separated. And in order to achieve the first order capacity, it is sufficient to encode each carrier separately. However, this does not hold for the general interference channel. There, it has been shown that it is the capacity region can be improved if coding is performed over the carriers. Now, if we go to multiple antenna systems, the situation changes also dramatically. For example, for the multiple input, multiple output, multiple access channel, we can still achieve the sum rate for any decoding order. However, if we want to optimize the weighted sum rate, the decoding order is important. And if we want to reach any point of the capacity region, again, time sharing is required. Time sharing is performed between different decoding orders. For the MIMO broadcast channel, we can also not directly apply the results for the degraded broadcast channel because the MIMO broadcast channel is not degraded. However, the capacity region of the MIMO broadcast channel is known since 20 years. Here we have to apply a technique which is called dirty paper coding. So for the MIMO broadcast channel, it is not sufficient to apply NOMA, that means superposition coding and successive interference cancellation. Instead, we have to use a technique called dirty paper coding, which allows us to use any of the two or multiple coding orders. And also very important, we have to apply time sharing. Otherwise, we cannot achieve the capacity region. Now, if we extend the thing, the multi-user network in terms of having multiple cells, we end up automatically in the interference channel scenario. And here we have different options of techniques how the base stations or the access points can cooperate. There are distributed schemes only depending on local data and local channel state information, coordinated schemes where base stations can talk to each other to decide on their strategies, cooperative schemes that exchange channel state information as well as data, and then there could be also one big cell serving all users one together. If we take a look at multiple access technologies in the history, we can see that the first and second generation mainly applied a technique called time division multiple access, so the users were served an orthogonal resource blocks in time. Then with the third generation, code division multiple access was introduced, a technique where the users can be either separated in an orthogonal way by orthogonal code sequences, or they can also have correlation and create interference. Then with the fourth generation, we moved on to orthogonal frequency division multiple access in a combination with a technique which is called spatial division multiple access. So here we are using different carriers to separate users in combination to exploiting the spatial dimension to separate users. And that is possible by applying multiple input, multiple output techniques. In 5G, NOMA was standardized for the uplink transmission, and now in 6G, we are again considering NOMA for the downlink transmission. And as a very new development, there are also other schemes called uncoordinated multiple access schemes like the grant-free multiple access, which has been standardized in the 5G New Radio Release 16. Now, how does these background information fit to the current development of novel network architectures? On the left side, we see the typical open radio access network architecture, where you have a central unit in the back serving distributed units which are connected to the radio units. Now, the radio units provide the wireless access to a number of user terminals. And you can see that this is not just a single one-hop network, but we have here a multi-hop network where we have data flows from the central unit to the receivers. And what tool can we use to characterize these systems? To obtain an upper bound, we can use the cut-set bound, which is a tool from network information theory as well. Now, there are schemes called multi-connectivity, which was standardized in 4G dual connectivity, 5G multi-connectivity, and a very recent development is the so-called cell-free architecture, where one user terminal is served by multiple radio units. And the techniques that are developed for the multiple access and broadcast channel are very well suited to achieve the so-called cut-set bound. And I have brought one example on the right-hand side where we can achieve the cut-set bound for a simple scenario with one central unit, two access points, and two users. If you want to get more information, please take a look at the corresponding publication. I just want to advertise two activities. One is the IEEE ComSoc Special Interest Group on Rate Splitting Multiple Access, where these techniques are currently discussed. And the second one is a pre-standardization group, which is called ETSI Industry Specification Group on Multiple Access Technologies. Thank you very much for your attention.